Welcome back, everyone, to another session on statistics. This is Muhammad again. If you remember last session, we talked about chi-square, different types of tests which enable us to analyze categorical data. In this session, we're going to work on a parametric test, mainly t-test, and its non-parametric version. So Uh, we want to work on a data set where we have two means, either coming from two different groups or from the same group over a longitudinal study or within subject study. And then we want to see how we can analyze these type of data. So what I want you to remember is that if you want to use a t-test, whether it's parametric version or non-parametric versions, we always have two means. And these two means either come from two different groups or the same group. These are the objectives of this session. So uh, you will learn how to compare two groups of participants using an independent sample t-test. Uh, You will learn how to compare the same participants over two occasions using paired sample t-tests. So we will learn about two different types of t-tests. You get to know what the assumptions are before doing any parametric t-test. So if one of these assumptions is violated, then you need to revert to non-parametric versions of t-tests. We will learn all about these in this session. Also, you learn how to report the results once you do the tests in Jamovi. Well, before I start talking about independent sample t-tests, I just want to recap again on the two type of designs. I talked about it in another session, but I want to recap before we start talking about independent samples t-tests. So if you remember, we had two different types of design: between subject designs and within subject designs. In the between subject design, we're going to compare two different groups, the mean of condition A and the mean of condition B. But in the within subject design, the subjects or the participants are exactly the same. So we test them once, and after some time, we test them for the second time. So that's why it's a within subject design. For now, I'm going to focus on the between subject design to analyze data from this type of design using an independent samples t-test. So what is an independent sample t-test? Some people call it a student test or a student's test. It's the most popular type of independent sample t-test. There are other types too, but this is the most popular one. We'll also see what other types are out there and then how we can use them. But once you have, again, uh, two conditions and you want to compare the two conditions, the means of the two conditions, then you need to use an independent sample t-test. I think that you have the data set now, PWA naming. In that data set, we have picture naming as the dependent variable, and also we have another variable called aphasia type, which consists of two levels. So in our sample, half of the people were people with fluent aphasia, and the other half were people with non-fluent aphasia. So what we want to do, the question is that we want to compare the means of these two groups. We want to see whether they're different in their picture naming latency or not. So this is the question we want to address, and then we'll see how we analyze that data. If you remember, before we start doing the statistical analysis, we always need to have a prediction. We always need to formulate our hypothesis. We can't just go blindly. because all statistical tests are based on the concept of null hypothesis testing. So that's how we state the hypothesis. So our null hypothesis is that mu1 equals mu2. Uh, Mu is basically the mean of the population. We are basically saying that the mean of population 1 is not different from the mean of population 2. In our example, our null hypothesis is that the mean of picture naming in the fluent group is not different from the mean of picture naming in the other group. And our H1 or our alternative hypothesis is completely different. Uh, we say that the means are going to be different. So once we state our hypothesis, we think about our criterion, the alpha level, which is always 0.05. I don't need to write it down here. And then we start performing the test in Jamovi, and then we'll see whether we can reject our null hypothesis or we fail to reject our null hypothesis based on the criterion we had, the alpha level we had, and then we report the results and we check the assumptions. So before we move on to the next slide, I don't want to talk about the equations because I told you at the first session that this is not about equations or the theoretical knowledge of statistics. But anyway, if you're interested in the equations and how a t-test, a t-score is calculated, you can find the equations here. One important concept in the t-statistic is the standard error of the mean. And the standard error of the mean is very similar to the concept of standard deviation. I think that by now you kind of know what a standard deviation is. Standard deviation was a measure of variability. Standard error of the mean is also a measure of variability. Is a measure of how accurately our sample is representative of the population, how accurately what we are seeing in our sample, the mean we are seeing in our sample, is a true representative of the population mean. And this is kind of captured by a standard error of the mean. So obviously, the lower the standard error of the mean, the closer our sample is to the population. So the bigger the standard error of the mean, it means that the larger the gap is between our sample and the population, and then probably we can't find a significant test result. I loaded the data into Jamovi, so this is our data set. I've kind of saved the latest version, so I don't need to change the headings anymore and the levels of measurement. So we're gonna focus on picture naming and aphasia type. We want to see whether picture naming latency is different across these two levels, fluent people with aphasia and non-fluent people with aphasia. So our independent variable is aphasia type. It has two levels, fluent, which is level 1, and non-fluent, which is level 2. And our dependent variable or response variable is picture naming, which is continuous variable. So we kind of check everything before we start. So you go to the t-test tab here, you click on t-test, and we want to do independent sample t-test because we want to compare two different means from two different groups. So there comes a window like this. So our dependent variable, as I said, is the picture naming latency or reaction time. Our grouping variable is our independent variable, aphasia type. So we want to compare the two levels when it comes to picture naming latency. So basically, once you put it, this is quickly, you could get the output here, which says that the means of the two groups are not significantly different. So this is a student's t-statistic, and this is the p-value. So what was our hypothesis? we go here and then we see the hypothesis. Group one was the fluent and group two was the non-fluent uh, uh, group. So our hypothesis was that the mean of group one is not different from mean of group two. So this was the null hypothesis. However, you could have some other predictions. You can have alternative hypotheses. So maybe your alternative hypothesis was that the mean of group one is bigger than group two, or the other way around. If you had those hypotheses, you can basically click on these ones and you'll see the values will change. But we started with a null hypothesis and we stick to the null hypothesis. But that's not always true. I want to emphasize that you might have some predictions which would lead to alternative hypothesis. So if you have an alternative hypothesis with two groups, you can easily modify the hypothesis here, and then you'll accordingly see the output here. So um, then we could also have some descriptive statistics, some descriptive plots. We could see that uh, uh, the naming latency in the non-fluent group is larger than the fluent group. So there's a difference here. That's the mean, the red circle, and the square one is the median. So we could see a difference if you also look at the group descriptives here. You could see that the mean of the non-fluent group is bigger than the fluent group. There is a difference here, but then our question is whether this difference is meaningful or not, is significant statistically or not. So that's why we have the alpha level. Our alpha level is bigger than 0.05, so we cannot reject the null hypothesis. So this difference here is not really meaningful. It could be by chance. It's not a statistically significant. So just like any other test we do, we always want to report effect size because of course uh, we see some differences, but here the difference was not significant, so the effect size doesn't really matter. But once the effect is significant, you want to say how strong that effect is. So in order to do that, we have an effect size measurement here, which is Cohen's d. So once you click on effect size here, you'll see that added to the table, which is here, is minus because it really depends on how you modify, how you formulate the levels here. Level 1 is fluent and level 2 is non-fluent. So that's why it's minus. If you change the levels, you put non-fluent as level 1 and fluent as level 2, this minus change to plus. So the minus and plus in the effect size and t statistic are not at all important. What is important is just the size of it. The direction is not important. So based on what we have here, we can interpret that the picture naming is not different in the fluent and non-fluent people with aphasia. That's what we could do, and then you could in the next slide. I'll show you how to present these results in a paragraph. That's how we present the results. We start with descriptive statistics for each of the groups. Because it was the data was continuous, we present the mean with standard deviation for each group, and then we uh, present our results. You could see the table I put there, and then the elements we need to present. We need to present the t-score itself, which is minus 0.94. Usually once the t-score is bigger than 2, we could see significant results. So here is a smaller than 2. That's why our p-value is not a smaller than 0.05. We also have degree of freedom. Degree of freedom in an independent sample t-test is calculated such as the number of participants in our group minus the number of groups. So we have 30 participants in our group minus 2, which is the number of our groups. It will be 28. So a t-statistic for with uh, 0.94 with a degree of freedom 28 is not as statistically significant. Once the results are not significant, we don't usually present Cohen's d or the effect size, but I just presented Cohen's d here so that you see how to present it. Otherwise, since the result is not significant, we don't need to present it here, but that's how we present it. And the minus or plus sign is not really important. Then after we present descriptive statistics and we present the results of our test, then we make an interpretation. So the interpretation of this result is that object picture naming is not influenced by the type of aphasia. That simple. Again, I emphasize as a disclaimer that this data is not real. So what you see here cannot be real. There are three assumptions which need to be met before we do the t-test. So these three assumptions are very important. So uh, one is normality, second independence, and homogeneity of variance. You need to make sure that your data from your sample is following a normal distribution. Otherwise, you need to do a different test. You need to make sure that your data are independent from each other, like people in group A are not participating in group B. So the people in group A and group B should be different. Otherwise, your data is not independent. And then you also need to make sure that the variance in group 1 is somehow similar to the variance in group 2. Otherwise, you cannot use an student's independent sample t-test. I mean the student's version. So in the next slides, we're going to see what we could do if one of these assumptions is not met, because this is not always the case where you collect data and all the assumptions are met and then you can easily do the test. Most of the times, the data is not normally distributed. Specifically, if you're working with reaction time, data is most of the time positively skewed. So you need to think about what to do if your data is not normally distributed. If your data are not independent, that's not very difficult. You can do a per sample t-test. If your data is not, it doesn't have the homogeneity of variance, then you also need to think about what other test you can use. In the next slides, I'm going to talk about them. So let's start with the last assumption. What happens once the homogeneity of variance assumption is not met? What happens if the standard deviation in the two groups is different? So we could use a different test than the student's test, which is called Welsh test. Uh, the way we calculate the standard error in the student's test and Welsh test uh, are different. So in the student's test, kind of the way we calculate the standard deviation estimate is kind of pooled. Everything is pooled. It's like you're averaging apples and oranges. But the way we do it in Welsh tests is completely different, which makes it robust against the violation of homogeneity of variance. Aside from this assumption, uh, the other assumptions have to be the same. Like in the Welsh test, the normality of distribution assumption has to be met, and the data have to be independent. So when it comes to normality of distribution and independence of observations, Welsh tests and students tests are the same. They're only different when it comes to homogeneity of variance. So most of the times I think that our groups do not have a the same amount of standard deviation, so we could safely use the Welch test. In the next slide, I'll tell you how to do it in Jamovi. Let's see how we could check the homogeneity of variance assumption in Jamovi. So we have the data here. Let's run an independent sample t-test. Just like before, we put the dependent variable here, independent variable here. So the result is not significant, but we want to check whether the variance across the two groups is similar or not. The test to check this assumption is called Leven's test. So a Leven's test is a test which checks the assumption of homogeneity of variance, and as the note here says, a low p-value suggests a violation of assumption of equal variances. So here the p-value is bigger than 0.05. That means that the homogeneity of variance assumption is not violated. In other words, the variances in the two groups are kind of equal or very similar. So we can proceed with this test, which is independent sample test, but let's imagine for now that this assumption is violated, and what are we going to do if this assumption is violated? So in the next slide, I'm gonna uh, teach you uh, what type of test to use if this assumption is violated. This is how we do the Welch test. So we load the data, it's the same data set. We go to t-test, independent sample t-test. So instead of a student's test, we select Welch test here, and then it's just the same procedure. We put the dependent variable here, and we want to compare the two levels in the aphasia type, and then we put it here. So again, when it comes to the Welsh test, the result is now significant. So yeah, this is how we do the Welsh test. So if you want effect size, descriptive and descriptive plots is exactly the same procedure we went through in the student's independent sample t-test. This here just you select Welsh test instead of the student's test, and then you'll basically see the same result. But uh, in this example, we see the same result, but this is not always true. Sometimes when you compare students' results with Welch results, the results could be different, but in this example, they're exactly the same. What happens when the data are not independent from each other? What happens once your design is within subject's design? Like you have a couple of people who attended the first session, you collected some data from them, and again after months, the same uh, people come and participate in the study, and then for the second time you collect data. So it's the same people who participated this in the study. That's why the data are not independent from each other. So you cannot use an independent sample t-test like a student's t-test or a Welch t-test. Rather, you need to switch to a different type of t-test, which kind of is designed to answer questions with this type of design where the samples are paired. Uh, we go through the steps of doing a paired sample t-test just like any other test. You need to state the hypothesis. Before we state the hypothesis, before we talk about the states, I want you to download the data. You should have downloaded the data so far. So we are working on the data PWA naming. For the paired sample t-test, we are working on two variables, anxiety before treatment and anxiety after treatment. So we had some people with aphasia who went through a treatment. We measured their anxiety before treatment and we measured their anxiety after treatment. And we want to see whether there is a difference between the means of the uh, two tests or not. And the null hypothesis says that the difference between the means, D here stands for difference, mu here stands for the population mean. So the null hypothesis says that uh, the, the mean of the difference equals 0. That means that occasion number 1, occasion number 2 are not different. But when it comes to the alternative hypothesis, the mean of the difference does not equal to 0. So we're expecting to see a difference in the mean. So uh, just like any other test, you need to have a hypothesis, and then you also need to have a criterion, which is the alpha level, which is 0.05 in our studies most of the times. And then I put also some equations here, how the t-score is calculated in a paired sample t-test. If you're interested, you can read more about them in the books I mentioned, but you don't really need to do it by hand because Jamovi will do it for you. But it's good to know how the equation works and like what all those um, signs are. And then we go to the data. We perform the t-test, paired sample t-test in Jamovi, and we'll see whether we could reject the null hypothesis or we fail to reject the null hypothesis. After all those results, we report the results just like any other test. And then again, we check the assumptions. We see whether the assumptions of the test are met or not. And if the assumptions are not met, then we need to think about other ways of doing the analysis. Let's see how we could do the paired sample t-test in Jamovi. So we have the data here. So we are going to see whether anxiety before treatment, which is a continuous variable, is different from anxiety after treatment, which is another continuous variable. And then the, the two variables are collected from the same participants. So the data is not independent from each other. That's why we're using a paired sample t-test. So we go to t-test, we use paired sample t-test. So we put anxiety before treatment, and then another pair is anxiety after treatment. And then we also use descriptive plots, and effect size. And this is basically what we want. So if we just go to the descriptive uh, plot, we could see that uh, our participants had higher anxiety before treatment. So once they went through the treatment, their anxiety decreased. You can easily see that in this plot. And once you go to the descriptive statistics table, you could see that uh, the mean before treatment was higher, and after treatment, it, it it decreased a little bit. And then the question is that now is uh, this difference occurred only out of chance, or is this difference a statistical difference where we could generalize to the bigger population? So we go to the paired sample t-test table. So we'll see that the p-value is significant, is below 0.05, and the t-statistic is 3.8. I told you that once the t-statistics goes beyond 2, whether it's minus or plus, it's usually a statistically significant. So this is 3.81, which is statistically significant. And we also want to report the effect size. When it comes to effect size, um, uh, we also use Cohen's d, which is here 0.69, which is kind of a uh, almost approaching a big effect, is a substantial effect. So once you report, yes, there is a significant difference, you also need to report how how big that effect is, and that is very important. And you can also only do it through Cohen's d. In the next slide, I'll give you some information about Cohen's d. But yeah, that is pretty easy how we do it in Jamovi, and then how we interpret the results. That's how we report the results. We start by giving some descriptive statistics like what was the mean and standard deviation before treatment, and what was the mean and standard deviation after treatment. And then we basically present the same numbers we got in Jamovi. We could present also the table, and then we will have our interpretation. So the interpretation here is that the treatment resulted in a decrease in the level of anxiety among the participants. So, uh, yeah, I mean, if you have two groups, if you have like a group with two means and the data is not independent, you can do a per sample t-test, and then you also need to report the effect size. The effect size shows how big that effect is, which here is quite substantial. The effect size ranges from 0 to 1. And yeah, I think that's fairly easy to do. Once you have the results in Jamovi, you just need to write a paragraph or two about the results. Again, I need to mention that this data is not real, so please don't think that this is true in your case. I just put a table here how Cohen's d is calculated if you subtract mean 1 from mean of the group 2 and divide it by standard deviation. Is very easy. You get the Cohen's d, which is a measure of effect size, and then how to interpret those values. You can see that I put a table here. So a value of about zero point 0.2 is a small effect, a value about zero point 0.5 is a moderate effect, and if it goes higher, then we'll see a large effect. So the Cohen's d ranges from 0 to 1. The closer to 1, the larger the effect is. We started with independent sample t-test, and we talked about three assumptions: normality of distribution, independence of data, and homogeneity of variance. So I told you that once homogeneity of variance assumption is not met, you can use the Welch test instead, which is robust against the violation of that assumption. If your data are not independent from each other, you can use a per sample t-test. But the last assumption I want to talk about is the normality of distribution in the sample. So there are basically two ways to check the normality: QQ plots and Shapiro-Wilk test. So I'll go first through the QQ plots, and like you can also see histograms next to them. So the figure here in the QQ plot you see here kind of shows a normally distributed data. I've talked about normal distribution a lot throughout this module. A normal distribution has two properties. The mean, median, and the mode kind of stand on the same line, and the tails are kind of symmetrical. So if the tails are symmetrical and the shape looks like a bell curve shape, then it's kind of normal. And once you look at the normal QQ plot, if the lines is kind of on the is diagonally going on the right line, then it means that it's not violating the normality of assumption. So I'll show you some other QQ plus where you can see that the line is not a straight line and the histogram is not a bell-shaped histogram. For example, look at this QQ plot and look at the histogram here. The histogram here is showing a positively skewed data. Is definitely the data is not normally distributed. The right curve here Let me show you here. The right tail here is longer than the left tail. The data is kind of stacked, is kind of clustered on the left side of the distribution, which shows a positively skewed data. So by just looking at the histogram, you can see that the data is not normally distributed. Also, if you look at the QQ plot, you could see that the line is not a straight line. The line should be straight line, just like this. The closer the dots to this straight line, the uh, more normal the distribution is. So you could easily see that we have a kind of a uh, big deviation from the uh, normality of distribution. So if your QQ plot looks like this, then your data is not normally distributed. And also, um, sometimes the data is kind of, we have uh, distributions which are very similar to the normal distribution, where the the bulk of the data is here in the middle, but the tails are very, very heavy. You can see that the tails are very, very heavy. So if you look at the QQ plot, you can see these dots here and here, which are kind of deviating from that straight line. These dots are kind of the outliers or residuals, which are beyond an acceptable level of deviation. So once again, once you see this type of distribution, again, with this type of QQ plot, it is suggesting that the data is not probably normally distributed, but QQ plots and histograms are one way of looking at normality of distribution. You can kind of complement that with a Shapiro-Wilk test. Let's see how we could check the normality of distribution in Jamovi using both QQ plots and Shapiro-Wilk test. So we have the data here, um, and then we click on t-test. We want to run an independent sample t-test. So picture naming latency is the dependent variable. Aphasia type is the independent variable. And then we scroll down a little bit, and then we see all the tests here. So we already looked at uh, the Levens test, which is a test to check homogeneity of variance, and it wasn't significant. That means that the variance across the two groups in our study are similar to each other. Now we want to look at the normality test. For normality test, the test we need to check is Shapiro-Wilk test, which W here stands for the Shapiro-Wilk statistic, which usually range between 0 to 1. So the closer to 1, uh, the better the normality of the distribution. And as you also see in the note, a low p-value indicates a violation of the assumption of normality. So the p-value here is not as small at all. So that means that our normality of distribution assumption is not violated in this variable. And also, we look at the QQ plot, we'll see that this straight line, these scores here are kind of lined across this straight line here, which kind of complements the Shapiro-Wilk test. So uh, you remember that when I was talking about independent sample t-test, I talked about three assumptions. One was normality of distribution. The second was independence of observations. And the third one was homogeneity of variance. So in this case, all of the assumptions are met. So we could kind of report the results of this test. There are also some non-parametric tests where, for example, the normality of distribution is not met, we could use non-parametric tests, or sometimes our dependent variable is just not ordinal, it's not just interval or continuous, it's just ordinal. So we could use non-parametric tests. So the non-parametric the non-parametric test for the independent samples t-test is Mann-Whitney u-test, and the non-parametric test for paired samples t-test is Wilcoxon signed rank test. So basically, if for any reason you can't do any of those t-tests, whether independent or paired, you could basically use their non-parametric equivalents or versions for like lack of normality of distribution or any other reason. In the next slide, I'm going to show you how to do them in Jamovi. In this video, I'm going to show you how to do the non-parametric versions of the t-tests, whether it's Mann-Whitney or Wilcoxon test. So let's start first with the non-parametric version of independent sample t-test. So we click on picture naming, which is our dependent variable. Facial type is our independent variable, and then you see the result of independent sample t-test here. So the Mann-Whitney u-test is just here. You click on it, and then you'll see the result here. So if if the normality of distribution is not assumed, is not met, maybe you could also think about using a Mann-Whitney U-test and see whether the results are different from the other independent sample t-test or not. Basically, other things like is exactly the same as independent sample t-test. You can get like all other like descriptive plus, effect size, and everything here. It's just similar. It's just a different type of test. So let's now move to the paired sample t-test. So we had anxiety before treatment and after treatment. We wanted to compare these two scores within the same population, and uh, it was significant, and now we just want you to demonstrate how to do it using a Wilcoxon rank test. And if you use a Wilcoxon rank test, it's also still significant. Uh, the the data uh, I just showed you, it was normally distributed, so there was no violation of normality of distribution. It's just here I'm just demonstrating you how to do them using Jamovi. Although the paired sample t-test and independent sample t-test we used were totally fine and okay with the data we had. So this is how we use Wilcoxon rank tests here, and the way we report them is exactly similar to the way we reported independent sample t-test and paired sample t-test. That's the end of this session, but before we end this session, let's review the objectives and see whether you achieved the objectives or not. So I expect you to be able to use both independent sample t-test and paired sample t-test. I expect you to know when to use each of them. I expect you to know what the assumptions are for any type of parametric t-test and how to check these assumptions in Jamovi. I expect you to know what the non-parametric versions of t-tests are and how to do them in Jamovi. And finally, I also expect you to be able to report the results of all these tests in your projects or in your studies. Please let me know if you have any questions. Write to me. I'll be very glad to hear from you for any questions or any feedback. Looking forward to seeing you in the next session. Bye bye.